Okay, they are quick enough, so they brought it. We have been discussing this matrix multiplication thing in systolic array. So this is what the DG was. Since I reserved the page, it saved us this time of redrawing the DG. So you remember this. I am multiplying two 2 by 2 matrices A and B, getting C. So A11 B11 plus A12 B21 gets to C11 here, so 0 here, so on and so forth. This is verified. So as such, the DG as given here is described by just 3 edges, one x direction, one y direction, z direction. Okay, 3 edges. But I told you that we can go further. We can go into the odd DG description and all that, whereby if it is the same location, we can assume as though this line carrying B is a separate line, has one branching node. This line carrying A has a branching node, and this line carrying the result has a processor here. And from this branching node, there is a small edge, and from this branching node, there is a small edge. All these are located at 0, 0, 0. And then we describe the entire thing in terms of a state diagram called RIA, regular iterative algorithm, where we find that around for A, between two nodes, there is one edge, 0, 1, 0 transpose. Sorry, for B 0, 1, 0 transpose. For A, in the direction, it's okay. This is B. For B 1, 0, 0, for A 0, 1, 0. Okay. Edges, then between A and C, from here to here, from here to also there are edges, but edges they are all located in the same place. So 0, 0, 0. Okay, same place. And then from here, if you go along, if you have to write this actually, this algorithm, where on the output side, on the left hand side, all these 3 indices will be same, I, J, K. Okay. So here you see there is an edge from I, J, K minus 1 to I, J, K, W is 0, 0, 1. And then we drew those equations, we wrote down those equations for the various edges. You assume that this edge for all the nodes, the schedule is what? S transpose the coordinate plus a gamma, this is B, gamma B. In this direction, at all the nodes, the schedule is S transpose the corresponding coordinate vector plus one constant gamma A. And in this direction, S transpose the corresponding edge vector plus gamma C. And then you get this equation that, okay, there is no communication delay, all that. So between this and this, there is an edge 1, 0, 0, S transpose just gives you S1 plus all the nodes in this direction have the same gamma, so gamma B. So gamma B minus gamma B, so it goes S1 greater than or equal to 0. Similarly, all the nodes in this direction, their schedules are S transpose the coordinate vector plus gamma A. Okay. Since the coordinate vector here, this edge here in this direction, you can see the edge separating the two nodes is what? 0, 1, 0. So that means if you take that vector as S1, S2, S3, only S2 remains because that gets multiplied with 1. So S2 plus gamma A minus again gamma A, because gamma A is constant along this line, for the nodes along this line greater than or equal to 0. For this, the edge is 0, 0, 0, they are all located in the same place. But you can assume, as I defined this gammas to C, A and B, that is why edge is 0, 0, 0. So S transpose the edge is 0, but gamma C minus gamma A. This is the scheduling inequality. Since the dependency is in this direction, this cannot start before this is finished. That is why this is greater than or equal to no communication, because the edges, even if there are some communication delay, these edges have no communication bottleneck because they are 0, 0, 0. So S transpose the edge plus gamma C minus gamma A. That must be greater than or equal to 0. The schedule here must not precede the schedule here. That is what it means. So you get this equation. This equation rather, because S transpose the edge is 0, S transpose is the 0. So gamma C minus A, gamma C, gamma B. And in the last case, S transpose this edge plus gamma C minus gamma C, gamma C minus gamma C. S transpose this edge will give you S3, this equation. You can choose your, so here gammas go, but here gammas remain. So you can take some gamma A and gamma B, and thereby you can choose gamma C and maintain those schedules and all that. But then for making life simple, I just consider the special case again where all the gammas are 0. So back to linear scheduling. Okay. where schedule is just S transpose the coordinate vector of a particular node, no gamma as threshold. Okay. Then from there I considered one example where like solving these equations, you can choose S1, S2, S3. We took S1 to be 1, S2 to be 1, S3 to be 1. Then in one example, for that S vector we found out one D vector, so that S transpose D is not equal to 0, because processors which are separated by D and map to the same processor, they must not have the same schedule. That gives us the equation S transpose D not equal to 0. So we constructed a D. Again, we did not take very high values of D elements, because otherwise efficiency will go down because S transpose D is the schedule gap between the nodes which are mapped to the same processor. So if that is too long, that means there is a too long an ideal state. So it was a particular D, and from that D we constructed one 2 by 3 matrix. Okay, and we proceeded. We will consider another example today. Okay, which also given by the name of this inventor of this. That is, as before, okay, D again has integer values. Earlier I took 1 0 0, H hardware utilization efficiency watts, S transpose D was 1, 1 by 1 1. You can have the same thing with this. Now my matrix P is that operator which works on a particular coordinate vector and maps it to a lower dimensional space, right? 2 by 3, you remember? In this case, P is a 2 by 3 matrix, n minus 1 comma n cross n, 3 to 2 dimensional transformation we are considering. P should be such that it has a 2 by 2 invertible submatrix and one extra column, 2 by 2 and then one extra column, because 2 by 3 is the size. But it should be done such that its null space, which is then spanned by only one vector, because if P has, as I discussed the theory in detail, if P is 2 by 3, but it has a 2 by 2 invertible, there is full rank square submatrix, the null space is spanned by only one vector. That is, if you have to solve for an equation like P x equal to 0, x will be general x will be just some multiple of one basic vector. Okay, this we discussed. Now I want to design P such that D happens to be that basic vector for P, that is the null space is spanned by P. Okay, you have got infinite choices. So 2 by 3, once again a 2 by 2 matrix I have to consider, which is full rank, which is the simplest is again 1 1 0 0, identity matrix is full rank. And in that case, what will be this? The general way of finding out, I told you a formula, but that is very simple. What should be here? So that this times D is 0, this times D vector is 0. See, identity times the 1 1 part, that is 1 1 plus this column times minus 1, that is minus of this column. Are you following me? Identity times this part 1 1, that is 1 1 again, times this column into minus 1. So minus column is equal to 1 1. So column is equal to 1 1. Minus column plus 1 1 equal to 0. So column equal to 1 1. So if you put 1 1 here, then you have this matrix. You see, now you do PD, you will see 0. Isn't it? But that means, what is this D? D is a vector, and where it is pointing? Which processors get back to the same guy? 1 1 minus 1. So from 0 if you go 1 here, 1 here, and then not plus 1 but minus 1, so you have to go down. So this vector like this, from this point to this point, this direction, that direction. Okay. That means this fellow and this fellow, they are mapped to the same processor, but others not, because in this case, since a 2 by 2 matrix multiplication, I have got a DG of this size only. There is nothing to paired with this, nothing to paired with this. If you consider a slightly bigger matrix multiplication, 3 by 3, 4 by 4, so there is a bigger cube, then you will have many more such pairs or processors which will be mapped to a single guy. In this case, just only these two can be mapped into one. You understand, isn't it? If you start with here, you go in this downward direction, there is nobody below this DG. Same everywhere else except for these two. Okay? But you can try just 3 by 3, you will see that some more processors get mapped to the same guy. Okay, same processor. So in general, you can see P times any coordinate vector I, j, k. Its pattern will be what? I plus k. You see this P times this I, j, k. I plus k, j plus k. Okay. This is a general pattern. So, we just consider the mappings and all those things now, edge mapping and all those things. Edge, there are three edges. One is A. A was originally what? 0, 1, 0. B. This edge E, PE and S transpose E, schedules. Okay, PE you can easily see. What it is doing? I plus k, j plus k. 0 plus 0, 1 plus 0. 0, 1. I plus k, j plus k. 0 plus 0, 1 plus 0. Am I correct? No. I plus k, j plus k, sorry. Yes, what is the question? 0, 0, 1. We put 0, 0, 1 here. This 1 into 1 is always there. No? 1 into 1, 1 into 1. This 1, 1. Okay. And schedule S is 1, 1, 1. So schedule is always, I mean, if all these vectors have only 1, 1, there is 0. So it will be 1, 1, 1. 1 means 1 delay. There is edge mapping. I am doing elaborately. The book doesn't give any elaboration. I mean, expects you to work out, which I am working out. So edge mapping and the coordinates, they need to be mapped, right? 0, 0, 0, that will always go to 0, 0. Any matrix times 0, 0, 0 is 0, 0. So that means this corresponds to 0, 0, 0. Now it is my direction, I in this direction, j. It is a two-dimensional world. So in this two-dimensional plane, what is the coordinate of this? 0, 0. Which processor is coming on? This guy. That I am indicating by 0, 0, 0. That is this fellow. Because P times this vector will be 0, 0 only. So it will be placed here. So now very quickly you can find out 0, what is this? 1, 0, 0. 1, 0, 0 will go what? I know general form, I plus k, j plus k. 1, 0, 0 will be 1, 0. So in 1, 0 direction, what comes? 1, 0, 0. Okay? Then this guy, 0, 1, 0 will be 0, 1. I plus k, j plus k. 0, 1. So this fellow 0, 1. So here, and this is 0, 1, 0 here. This guy will be 0, 0, sorry, 1, 1, 0. That means 1, 1, 1, 1. Same is this fellow. As I told you, these two fellows map to the same processor. You can easily see its coordinate is 0, 0, 1. 0, 0, 1 also, 0 plus 1, 0 plus 1, so 1, 1. So here actually two fellows come. What are those two fellows? 1, 1, 0 and also 0, 0, 1. Okay. So I am left with this, I am finished with this plane and this guy. This guy, what is the coordinate? 0, what is this? 0, 1, 1. So 1, 2. 1, 2. 1, 2 here. And this is what? This fellow. 0, 1, 1. Okay, still this fellow, this fellow. This is 1, 1, 1. 1, 1, 1 means 2, 2. And this fellow 1, 0, 1. 2, 1. 2, 1. Please follow my lectures carefully. Book gives a more general array with many processors and all that. You may get confused. I will draw the array like only this, nothing more. Also, book doesn't explain these details of functionality and all that, how the data will be or arranged in various processors and all that. Okay, we need to examine those. Then only it is complete. It is not just conversion of one diagram into another diagram, which all these transformations are. Okay, you have to make them realistic using the properties of digital hardware and all that. Okay. So this was what I have forgotten. This was 1, 0, 1. A11 comes here, and now give the edges. Between this and this, there are edges. All edges have delay. One delay. Between this and this, 0, 0, 0, 1, 0, 0. So there is an edge. This one delay. One delay. Okay. Similarly, then this here, same edge, whether in this direction or this direction or here, you have the same edge. Are you getting me? This one, these vectors are same now, the same edge, 1, 0, 0. So S transpose that, which gave me 1. So this edge is, they all have 1 delay. Now another direction, this was 0, 1, 0, isn't it? 0, 1, 0. So that could be here also, here also, here also, here also, 4, linking these processors. Okay, 0, 1, 0 was giving rise to you can see one thing, 0, 1, 0. First we did what? 0, 1, 0. Oh, just a minute. First I made the mistake. First we did the other way, 1, 0, 1. Yeah. First we did 1, 0, 1. If you do p times that edge, you get 1, 0. So edges are in this direction. That is why this edge, that I stated even otherwise also. I mean directly just using the analogy that all these edges, they will map to the same thing. Whether the edge is here or here or here or here, they all map to the same thing, which is given by p times this edge, which is 1, 0. So 1, 0, 1, 0, 1, 0, 1, 0. Okay. All right. Similarly, we consider the other top one, A 0, 1, 0. This one, this one, this one, this one. 0, 1, 0. P times that is 0, 1. 0, 1 means 0, 1. So in this direction. You can easily identify that 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0. These two processors had an edge. So corresponding two processors, this edge in this direction. Okay, this way. Again, schedule, if you see, it is delayed. So all these edges have single delay. Okay. So far so good. But then I have to see how the array is working. It's not like just transforming a figure and leaving it there as the book does, because I have to see the data arrangement. Theoretically, you can see A11 comes here at the time, at some time, that will be scheduled at S transpose this plus no gamma, so 0 0. So A11 hits this guy, say 0th cycle. S transpose this coordinate. Oh, I have not finished with another edge, sorry. See, this fellow was there. There are 3 edges. I finished with AB. C have to consider 0 0 1. That was corresponding to the vertical ones. C. This one, this one, this one, this one. P times that edge is 1 1. 1 1 is this direction. And again, that has a delay. You can now easily see data movement. Instead of doing all the theory, just using our common sense of digital hardware, we can tell you A11, B11, they pumped in here like this guy, this is that processor, it takes A11, B11 and 0. 0 I am not showing, 0 it is taking to compute the result. If you want, you can show 0 here. All these are zeros. Huh? So A11 times B11. Then the result moves in this direction. This direction is this direction. So cycle number 0, here I produce A11, B11. Cycle number 1, that moves here. Cycle number 0, I produced here the other data, this A12. So cycle number 1, it comes here. Cycle number 1, I produce here B21, this data, these two. So after one cycle, cycle number 1, this moves here, this moves here, A12 times B21 plus what we obtained here previously, that gets added. So result comes out here. Here something you have to understand. This is where the problem is, because this represents 2 processors of the original space. This is first representing this guy, A11 B11 plus A12 B12 final result here. So the result comes out. In the next cycle, it will assume the role of this. Flip flop will be cleared. There will be flip flop to store the result. That will be cleared. Again, so new computation will start with 0 like this here. Okay. It will not assume previous result. Previous result is finished here. That result will not be used at this processor. So those extra things you have to do. There is the engineering you have to do. You have to clear the flip flop here. It will not store that result. It will give a 0 to new computation as initial condition. Okay. That's okay. Sorry, you draw these also. Huh? So remember the cycles. Cycle 1, this result comes out. Cycle 1, what happens here? B11 has come here, and that time I give next guy. Next guy is A21. So next cycle, cycle number 1, A21 into B11. Second row of A times first column of B, A21 into B11. Result is obtained here, cycle number 1. Then it moves here in cycle number 2. That times what comes? It was in cycle 0, 1 here, 2. So B21 has come here, and this has to have a data, and that data is A22, cycle 2. Okay, so in cycle 2 I give A22. So A22 into B21 is the result A22, just a minute. Yeah, A22 into A21 into B11 and then A22, second row of A matrix, A22 into B21, that result comes out here. Are you following? This timing analysis is very essential. Mind the books, some of this book does not describe this, but this data arrangements, which data to give where in which cycle, this is very important. Otherwise, everything will collapse. So cycle 1 result comes up here. That times this moved here, and A21 times B11, cycle 2 it comes here. Then that time B21 into A22 result comes up cycle 2. Then what else? One result obtained here, one result obtained here, and two more results. One will be here, one will be here. Here what is happening? This I gave it cycle 1. This was moving here. B21 into A11. A11 cycle 0, cycle 1, if it comes, sorry, it will be the next guy, B12. A11 was given in cycle 0, so was with B11, B21 also. So A11, B12. A11 has moved in cycle 1 here, B12 has been given A11 into B12. First row of A, second column of B. A11, B12, that moves here. Next cycle, there is two cycles. What comes up? A12 comes down. That times I have to give a data here, which is B22, cycle number 2. That result comes up. So likewise, which is a fully pipelined array. There is a delay in all the edges. Critical path is that of the node, this processor. Very symmetric, very regular. Okay. So these two examples, there are some more examples given in the book. Arrays also are not shown. You can try yourself. So I will not go into this systolic array examples anymore, but there are plenty of things one can do. You can do Google search or IEEE Explore search. See, you can implement them in your projects also. You can take up projects, implement them, like systolic array for FFT, DFT, DCT, DCT. You know, there are plenty of works. You can implement them on FPGA. It's very nice. You can see the advantages. From here, I move into another topic where systolization techniques, those transformation others will come handy. Okay, and that is the reason why I considered the topic just before this. It is called bit level architectures. Bit level, in fact, I would say first we will do bit level arithmetic, like multipliers, those kind of things. How to make a fast, efficient multiplier, systolic array for multiplying to 2's complement number. I will derive that actually. Then we will be using them in bit level relation of digital filters, like bit serial digital filter. You are familiar with in all your DSP, whatever you studied, that is our bit parallel. X of n minus 1, all those are words, 16-bit words or whatever, they come in parallel, those are bit parallel. All your Oppenheim-Seymour DSP, that is bit parallel. But we can consider bit serial DSP. So there again, bit parallel architectures will be two-dimensional. The DG will be two-dimensional. To make it, bit serial, you have to transform it from a 2D DG to a 1D DG. Where all these things. It will become one-dimensional structure. So this systolization thing and this transformation things will come handy there. Those are bit serial digital filters. Bit serial will require less hardware, but we will need a faster clock because you have to put so many bits serially. I presume you know this number representation 2's complement pretty well. But nevertheless, I have to go through that motion, and that time we will see how much you know, or whether you know certain things or certain things you do not know. Also, it depends on how one presents. Okay. We will be considering 2's complement system. The particular format that we are taking here is that you will be given a number like this, a W bit number, that is length, W length, the order actually. These are the bits A, W, W or W minus 1, W minus 1. Here you assume a binary point. That is, we will be dealing with basically all numbers, you know, which are less than 1 in magnitude. Because normally we require that in DSP. Because you know what happens if you are multiplying two numbers, if multiplied as such, the result can be bigger, and there can be overflow. If the number of bits is less, you won't be able to hold it, repeat it using those few bits, overflow can occur. But if the numbers are preconditioned to be less than 1, when you multiply them, it is further less than 1. So overflow will not occur. So there is a DSP, this normalization usually done cleverly. The multipliers are normally, so that they are less than 1. So that is, we will follow that convention. So there is a binary point. This is called a sign bit. Okay, all this AI is either +1 or -1. Sometimes I will take them as binary, sometimes I will take them in the decimal sense. Then in 2's complement, what is the decimal value of this? You all have studied 2's complement. What is the decimal value of this? Here. Under 2's complement representation system, I have not told you whether it is +1 or -1, +1 or -1. General word is given to you. This you do not know, because you are taught digital electronics in a very simplistic way, I define, see, you follow the way I teach, okay. I am proposing as a number system. It's not that I am proposing for the first time, but suppose I am introducing. I am proposing a number of representation system called 2's complement, where I take words like this. Each symbol can take as a +1 or -1. Then I say, this is my definition, I say that its decimal equivalent is minus this number, and then now it could be 1 or 0. Now you treat it as decimal number, 1 or 0, plus the binary, the decimal value of this, which is how many? Okay, this part. Don't worry, all the things that you are familiar with in your digital electronics, they are all contained in it. I will explain all those, but just be with me. I am proposing a number representation system where, given a word, I say its decimal value will be like this. I call it 2's complement. It could be a new kind of 2's complement. So you don't confuse with your 2's complement to start with. Okay. Are you following this? No? This is just a if you put a binary point here, then this has weight 2 to the power -1, this has weight 2 to the power -2. So if you do this, but this is the decimal, pure decimal equivalent of this part, if you forget sign. Only for this part, I am multiplying by 2 to the power -0 or 2 to the power 0, which I don't show. This is the number. What it means then, that if this is 0, sign bit is 0, then 2's complement is nothing but simple decimal equivalent of that number. Okay. If sign bit is 1, then what is happening? You start with all 0 first, 1 and all 0. That will be what? -1 plus 0, that is -1. Then from all 0, you make it, you just go one step ahead, 0, 0, 0, 0, 0, 1. So, it will come down -1 plus only this part. So, it will from -1 it will start coming down, and finally a stage will come when all are ones. So, -1 plus 1 times this, 1 times this, dot dot 1 times this. So, we will get I think very small number, negative number with very small magnitude, minus half, minus, I can't make it out, but very small number. Those are the minus number, they will be covered by this representation. So, by this definition I am covering a range. What is the range? A range of numbers, a discrete set of numbers in a range. What is it's a discrete set, either this or that kind of thing. What is the range? When it is 0, how much is it? 0.111111. What is that value? If I go, come on, 0.1111 up to 1. How many bits here? W minus 1 bits. What is the result? What GP? Come on, you should be able to use your intelligence. 0.111. If I just add a 1 here, what do I get? So, 1 minus, that's all. Why GP and all that? This is smart thinking. I am sure you guys are very smart. You can do it. But I just wondering. So, this is 1 minus, range is 1 minus 2 to the power this thing. This is on the positive side. And negative side is, I told you, when it is sign bit 1 and all are 0, then it is maximally negative -1. The moment you start giving more numbers here, then what happens? From -1 it starts coming down because of this contribution. The final when all are 1, then -1 plus 1 into this, 1 into all that stuff. Basically it will be this, because 1, 1, 1, 1, 1, that is giving rise to this, isn't it? It will be a negative number of this magnitude. So, this is the range. Range is, closed interval and all that. That is I am putting. So, in this range, this is a discrete set of numbers, decimal numbers. In fact, you can decimal numbers, yes, and those that are covered by this representation. This is my definition of this. I am giving a definition. The word will be has to be interpreted this way. Whenever you get this, its value should be this. Then immediately the question comes: why the hell I am doing all this? What do I get? Isn't it? What is the motivation? See, you may have studied these things little bit, indeed, but please be understood that you have not studied much. Why 2's complement? What is the advantage? You do not know, and I am not blaming you for not knowing it. In this course, after some time you will learn. Though it is not the purpose of this chapter. My purpose is not to teach you 2's complement, but this is required. If I develop some parallel multiplier, systolic array multiplier, for multiplying 2's complement numbers, some property is required. So that is why. So as a byproduct of this thing, you will learn about 2's complement. So okay, what do I gain of by this? Before I consider the gain, just I assume that okay, you gave me a number A like this. You said that we have adopted a 2's complement system and 2's complement system is defined here, and you gave me a number A. I don't know whether it's 1 or 0, 1 or 0, 1 or 0, A. Then first thing is, what is minus A? Minus A will be, if A is this, its decimal value this much, minus A will be minus of this decimally. I am down in a, please don't get confused. Sometimes I am writing equal to and all this, I am doing decimal arithmetic. Sometimes I move to binary, you will be able to understand. This is purely A is represented decimally, so minus A means minus of the entire stuff. So I am putting A W minus 1, minus goes, and this thing, this I am writing like this. Is this correct? See, Chakra? This summation I am writing compactly. I equal to 1, so W minus 2, I equal to W minus 3, like that. I goes from 1 to W minus 1, simple. So this is your minus A. But then I can now do something and get some, simplification. What I will do, instead of this A, this is all minus, so permit me to put a plus here. So obviously I have to cancel it out. So I cancel it out here. What is this summation? To the power, now you can use your GP and whatever you know. So what is this summation? GP is something I am not very confident. To the power minus 1. How many terms I have? To the power minus 1, to the power minus 2, dot dot dot, to the power I have forgotten. How much? If you put a plus 1, minus 1, this is GP, of course. How much? Huh? Is it W or W minus 1? Okay. That is this. So bring this back here, there is a minus sign. So that means this will become minus 1 plus this. Minus 1 plus this, because there is a minus sign here. So that minus 1 I will put here. This remains as it is, plus and now gentlemen, if this was binary 0, this quantity is 1. If this was 1, this is binary 0. So I can put a bar here, indicate complement of that bit, and again taken decimally, because it's a decimal expression. Take the bit, complement it first, and then again use in a decimal computation. Okay. Same thing I can do here. These are all 1 minus stuff. Okay, 2 to the power minus I plus 2 to the power this. What is this much? This is the 2's complement representation, decimal value of the 2's of what? In the 2's complement definition, as per the 2's complement definition given by me, this is the decimal equivalent of a particular binary word. What is that word? Whose MSB is A bar W minus 1 followed by A bar W minus 2 dot 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 up to A bar 0. Okay. To that is you are taking the word complementing each bit. That part has this much decimal value by my definition. To that you are adding this decimally, means binary wise at the LSB you are adding a 1 to the power minus W minus 1. What location it is? You know, to the power minus 1, to the power minus 2, to the power this. So to this LSB you are adding a 1. This is what your family you are told that okay, if you have to take 2's complement, you complement all the bits and add a 1 to the LSB. Binary 1 to the LSB. Is it? So that's what I prove here. The negation is very simple. As per my definition, if you go by my definition of this thing, 2's complement and all, negation is very simple. Just complement all the bits and add a 1. to the LSB. This is number one advantage. But main advantage is under 2's complement, as you can see, suppose there are two numbers A as I am considering same word length W. You can choose defined word length also, but I am just taking. Sorry. I don't know what these bits are. So, therefore, what is a negative number or positive number I don't know, because I don't know the sign bit, I don't know other bits. But one thing is there, suppose you are adding, firstly if you are adding two numbers in 2's complement, what will be doing? You will be adding this with this. 2 to the power minus 1, take common this bit, 2 to the power minus 2, take the two corresponding bits, add. So, basically it is just addition of this entire part, which you can do in the binary way. You will get the same result. Whether you first convert in decimal and add and see decimal, or you keep it in binary, add and then convert in decimal, you will get the same result. That is underneath. If instead of b, if you have minus b, and suppose you are subtracting, you are doing a minus b. I am saying subtraction is not required. That is the advantage, which also you know, by the way. Under 2's complement, I don't need any subtract, because if it is minus b, what is minus b? It is again a form like this, but only thing is there will be just instead of bw minus 1, it will be this. Okay, and then there is this term and another extra term. Okay, plus that 2 to the power what? Minus. So, that means if you want to do a minus b, classically you needed a subtractor, subtract b for me. But here I am saying minus b also is these forms. If you want to do a minus b, it is nothing but a plus within bracket minus b. There is this plus this, and when you add them, you see this part, you just take the 2 to the power minus 1 terms, add together. 2 to the power minus, that is what you do in binary. Only thing is the LSB have this extra another 1 bit coming. Okay. So, understand that in 2's complement system, since negative also takes this kind of form, negative of the number also takes this kind of form, it is just complement of beta, nothing else. You can do all the job by simple adders, no subtractor is required. Okay. This is what I thought, I mean, we can expect you to know, and you know it, of course, in not maybe in this a very formal way. This is the proper way of 2's complement system. But there is another major reason why 2's complement system, became such a success in many applications, especially DSP, communication, all that. That is, suppose you are adding many numbers, like in a filter, if you carry out convolution to find out current term, naturally, so many terms are added, W0HN, sorry, W0XN, W1XN minus 1, W2XN, all these terms are to be added. So, there are 100 such terms, and they are all in 2's complement. Okay, they are initially not in 2's complement. Now, it can so happen that when you add the numbers, the result is so high that there can be overflow. That is, you give me 16 bit for all, but 16 bit is too less, there will be overflow, and therefore, I will have inaccurate result. So, that is a possibility. Now, suppose I tell you that for by some way or other I know the result, final result will be within the range +1 to -1, +1 to -1, because I told you overflow means it should not go, exceed the given range. That is, the MSB should not be pushed to the left and there should not be flowing to the MSB and all that, we sign bit and all that. Okay. That means if the number is in the range 1 to -1, then there is no overflow. Suppose I give you the guarantee that look, you are doing this filter output computation, so many additions, fine. By hook or crook, it is guaranteed that the final output is between 1 to -1. Even then, you can get classically, if you are not using 2's complement by other systems, you can have trouble in the sense you are never adding say 100 terms together, you always add 2 at a time, then this result with the third guy, result with the fourth guy. suppose intermediate sums have overflow, but some intermediate sum can shoot up so much that if the final result is less within 1 to minus 1, intermediate result is high and not representable in this 16-bit manner. So that will carry an inaccurate result because overflow has taken place in the intermediate stage. So that will surface in the final result will be wrong usually. But under 2's complement, this is beautiful mathematics, you know. If you can, I mean, I am not showing it here. I mean, if you can give a guarantee that final result will be within that range 1 to minus 1, then if all numbers are repeated in 2's complement, you can just close your eyes as far as intermediate overflows are concerned. Let them be. They will not affect your final result. Isn't it beautiful? Intermediate overflows, yes, let them occur, let them give wrong result, but final result will be correct. That's mathematics, beauty. That's the main advantage of 2's complement. I'm sure you didn't know all this. We'll be in the next class, we'll be considering multiplication of numbers, 2 W length numbers in 2's complement, and then we'll develop some systolic arrays and all those, and then again convert them into bit serial form. Then we move to digital filters, bit serial, where these multipliers will be used, serialized multipliers. Okay. So that's all for today. Thank you very much.